Hello, everyone. Welcome to MIF++. So it's a pleasure now to introduce Felix Therrien from Mila Institute in Montreal, Canada, who will talk about accelerating materials discovery with application-focused machine learning. Over to you, Felix, please.
Thank you. Hi, everyone. So thank you for the introduction. So I'll talk about how we try to apply machine learning in a way that will be relevant for applications, but also for experimental realization. So I'll talk about concept of the inverse design, and then how we can generate molecules or materials, and then I'll go into 3 applications. So we have 2 applications related to catalysis and then one related to battery materials. So let's get into it. All right, so typical materials discovery workflow works sort of this way. Okay, so imagine you want to find new molecules for OLEDs. So these are display materials that are blue. This is typically a harder problem. So you would start from your knowledge or your experience of what you think could be a good candidate material, and then you try this candidate material in the lab, and then only once you've made this material, you can verify if it has the property that you want. So you can verify if it's blue, and then most likely it's not. And then so you have to start over and try a new candidate. And that works very well. Most of the things that we have discovered so far were discovered this way. But for some problems, like climate change, there's this sort of urgency to discover new materials quicker. So a long time ago now, people started thinking, okay, can we accelerate this process using a computer? So in this paradigm, the goal is still to discover, in this example, blue OLEDs, but instead you start from a database of existing molecules or materials, and then you use a theoretical model to predict this property, and then you go through the database and you see if you can find materials that have the property you want, and then you identify the ones that you think are going to be blue, and then you realize those in the lab. So you're bringing the step where you check for your property a little bit closer to the beginning. So in the inverse design, the paradigm, or that in often cases is the machine learning paradigm, the goal is to bring this step of the property at the first step. So saying, I want to generate materials that have the property I want, that are blue. And then directly, the next step is, okay, we have identified candidates, we can try them in synthesis and in the lab. So obviously, in real life, you still need all the other steps that you had before. So now you have this sort of workflow, which I think is the modern materials discovery workflow and AI accelerated materials discovery. You start with a machine learning model that generates materials or molecules that are supposed to be blue or supposed to have the property you want. Then you can do an extra step of checking if the theoretical models agree with that. But now you don't have to go through a whole database. You go through materials that you already think are going to be good. And then you realize these materials in the lab, and you obviously still have to check if they have the property you want. And then every time something doesn't work, you can learn from that mistake and improve your machine learning model. And then hopefully this whole process accelerates materials discovery. So at Mila, this is what we're trying to work on. This is like our end goal. So now I'll talk about this generation step. Okay, so a normal neural network works this way. You've probably seen images like this before. This is an image of a neural network. So you start with some input data. So those are the circles in red. And that could be images. That's the typical ML way. But for the cases that we're interested in, that can be crystals or molecules. So that's what you input. And then you have this output that is a label on this data. So for each image, you have a class this is an image of a dog, this is an image of a bird. For each crystal, you have some property like formation energy, and for the same for molecules, you have a property attached to each of the molecules. So at first, you go through this network and you obtain some result. That's the gray point at the end, and then you compare that to the label, and then you get the gradient with respect to your parameters, which are shown in blue, and then you update your parameters.
Felix,
So yes,
could ask here a question.
of
This
course.
formation energy, is it an experimental property like emission color, which is probably experimental, or is it theoretically computable?
So for formation energy, it's theoretically computed. Those are just examples of labels, though. You could have any types of labels. But for crystals, formation energy is a pretty typical energy. Like that's, a lot of MLIPs are trained on formation energy. So that's why I put it here, but really it could be anything. The labels could be theoretical, the labels could be experimental. The labels could even be from other machine learning models.
And for example, when you synthesize or would like to check this property, can this formation energy be experimentally checked?
Well, not directly, but you can check if a material is stable. Formation energy should give you some sort of estimate of stability, like one phase is stable versus another phase. So you can know if a phase is stable, if it's realized, if you have some sort of composition and you get one phase versus another, well, you know that the one you get most likely should have the lowest formation energy. Not necessarily, but it's a proxy for stability.
Okay, but emission color is more measurable experimentally, right?
Yes, of course. Yes, that's the direct measurement.
Okay, thank
There
you.
are some properties like that that you have are easily measurable in experiments, and others are not. And that's very interesting. I think we'll see more of that in this talk, but there's ML, and then there's theory, and then there's experiment, and there's miscommunications between each of these steps. Yeah.
Okay, thank you.
Okay. So a very simple way that you can use a neural network to generate things is to do input optimization. So now, so what's shown in blue is what you optimize. So now, instead of optimizing the weights, you're optimizing the input. So you're trying to say, okay, I'm going to optimize the images themselves, or the molecules, or the crystals themselves. And now the thing that you're comparing it with is actually what you're wanting. So let's say you want a specific class. You want this image to look like a dog, or you want a specific energy. You want to minimize this energy. You want it to be as low as possible. Or you want a specific band gap, which correlates with color, for example. So in typical machine learning for images, because this is a very simple idea, it's really just the same mechanics as for training a neural network, but instead of changing weights, you're changing input. This has been done a long time ago. This is a 12-year-old paper where they do that for images. So they had a classifier that would take in an image and then say what type of animal it is. And then they did this in inversing scheme to see what happened if you optimize for, I want this class. So these look a little bit like geese, and these look a little bit like wolves or dogs, and these look a little bit like cubs.
Felix, did you mean that this indeed optimized goose and cup images? So it's not some sampled images.
No. So they trained a neural network to classify. So the neural network is trained on, here they would have seen images, and so like dogs and geese, and then at the end they would classify. They would say this is a dog, or this is a goose, and then here they use this process. So they gave it goose, and then they optimize this input, and then they get this sort of noise that looks that has some features of the class, right?
But don't we expect to see the best possible, say, cup image?
Ah, well, no, that's a good question. So, you know, the neural network doesn't learn perfectly what
Mm,
what a goose is.
mm,
It learns to recognize patterns of goose, and that's sufficient to be able to make a good prediction. So when you inverse it, you also sort of see all the limitations of this network, so the idea of this paper is like interpretability. Try to understand what are the things that the network identifies as being like from a goose. So the idea is, can we do the same with molecules? So for images, we have pixels. For molecules, what we can use instead of an image is a graph representation. So a graph representation, this is a very simple molecule. This is a graph. So it shows how each of the elements in the molecule, so each of the atoms in the molecules are bonded together with a type of bond that forms a graph. You can represent that as an adjacency matrix, which shows the bond or the link between each of the atoms in the molecule. This is N and C are bonded with type 3. And then each types of elements in the molecule. So here we have 3 atoms, 1, 2, and 3. And they each correspond to a type with what's called a one-hot encoding, where you have zeros everywhere except at a position that corresponds to a specific element. So this is a molecular representation. So now we've converted some like a molecule into numbers. Sort of like we can, when in an image, you convert something that's real into pixels. So yeah, now if we want to invert this the same way we did for images, how do we guarantee that we make a good molecule? So as you've noticed, the geese don't really look like perfect geese. So how do you get from this to something that looks more like what you want? And of course, we have the same challenge for molecules. We don't want really to get something that looks like an adjacency matrix. We need something that is an adjacency matrix. So that is something that looks like an adjacency matrix. It has the same shape, but you know, an adjacency matrix needs to be symmetric. There needs to be 0 on the diagonal. So how do we guarantee these things? Well, okay, so what do we need exactly? What are those rules that I'm talking about? Well, first, we need to use an explicit representation of the adjacency matrix. That's easy. Okay, let's use that. Then we need this matrix to be symmetric and positive with 0 trace. Okay. It needs to be integers only because the bonds are there's bond types, then they're not floats. They're actually, you know, they're integers. And then all the values need to be smaller than 4 because that represent valence, and you shouldn't have a valence of more than 4. Then for the feature vector, what do we want? Because we're also optimizing the feature vector. Well, that one is easier. It's a one-hot encoding, so the only rule is we only need to have one for each row and nothing else. Everything else should be 0. And then, of course, we want some chemistry rules to be respected. You know, you can't have a hydrogen atom that bonds 4 times. That doesn't make sense. So we know what valence each of these atoms should have. And so we want that to be respected. So I won't go into the details of how we do this, but basically we add an extra step. Instead of directly optimizing the adjacency matrix, we optimize a vector and we construct an adjacency matrix from that vector. And then we guarantee that the construction will always lead to something that follows the rules. So we construct an adjacency matrix that's always going to be symmetric and positive and have integers from this vector that is the thing we optimize. And then as for the feature vector, we construct the feature vector from the adjacency matrix in a way that will guarantee that the chemistry rules are followed, which means if in the adjacency matrix something has 3 bonds or a valence of 3, then we know that it will be nitrogen. So if we add all the bonds for each row corresponding to each atom. Here we get 4 bonds, so we know it's going to be a carbon atom. And if it makes 1 bond, then we know that it's going to be hydrogen or fluorine. And so by construction, we guarantee that those rules are followed. Then, as for respecting the rules of not being more than 4, we use 2 strategies here. It's not super important, but basically we add an extra penalty to the loss, and then we make sure that once we're below 4, there is no way to go above 4. And so in the end, with these pretty simple construction rules, we're able to guarantee that the adjacency matrices and the feature vectors will make sense. And then, so we can generate molecules. So all we need to do is train a network to predict some property. Here it was band gap. And then we start from an existing molecule, and then we just optimize it. So we optimize its adjacency matrix and feature vector to get to the property we want. So if you look at each of these little videos, we start at a certain distance from the target band gap, and then we start iterating, so optimizing, and then you can see that we get closer to the target until we get within some threshold, and then we can stop the optimization. So we start from a random molecule and get to a molecule that has the property that we requested, basically. And you can see here there's three examples of that. And of course, this is slowed down, so you can see it. In reality, it doesn't take much time. So what that means is we started from a predicting model. So it's just a graph neural network that predicts band gap. And without additional training, we can use this to generate molecules. We can use it to generate materials that have the property we want. So we did the extra step of now verifying, if we use band gap as a test, if the predicted band gap of these molecules that we generated was actually in DFT, the band gap that we requested. So this is a parity plot. You have the predicted energy on the y-axis and the DFT energy on the x-axis. So we had 3 objectives. That was around 4, around 7 EV, and around 9 EV. So on the y-axis, you can see that the proxy model, so the machine learning model, was always within 0.1 of the objective, which is the stopping criteria. That makes sense. And now once we measure these molecules, you can see that their distribution, the DFT predicted property, is centered at the property that we want. So it's not perfect. They're not all like exactly on spot, but they are mostly having the property we want. So if you imagine the scheme from the beginning where we do filtering, now we get to a set of molecule that is much more likely to get to the right property. Okay. We compared that to other models that did similar things, but used more training, and they get similar generation quality, and you can see that the distributions are similar for these state-of-the-art models. But we did this really only using a predictive model. Okay,
Felix,
so the takeaway. Yeah, sure.
May I ask if the output is a molecular graph, or do you embed your atoms in a three-dimensional space?
Yeah, that's a good question. So the output for this model is just a 2D graph, which means it's not embedded. It doesn't have 3D coordinates. But because those are pretty simple molecules, the embedding is sort of easy to guess. So you can use RDKit to get an embedding that's pretty good. And then when you put that in DFT and you relax it, then you get, I think, to something that's pretty realistic. But it does play a role. It's true that, that is part of why there is spread. Yeah. So the takeaways from that, the main takeaway is, if you have a predicting model, you can use it to generate molecules or materials. It doesn't need to be the way we did it. We did it directly with just the predictive model. But in machine learning, it's sort of true in general. If you have this model that can make predictions, you can generate molecules, you can generate materials. And then the other takeaway is the predictors and the objectives, they need to be robust, because if you look at the performance of the machine learning model at predicting band gap, it's actually very good. This is a parity plot. This is the same axis as this, but if you look at the performance, the spread becomes much larger on generated molecule than it is on the molecules from the data set that the machine learning model was trained on, which means that the predictive model, the generative model, will tend to sort of trick the predictive model into giving it unreliable predictions. So we always have to be careful about that. Okay, so now coming back to this, scheme that we're trying to achieve. Now we know that this ML part, here I presented you did gen, which is a direct inverse design generator, but you can use a lot of different machine learning models to do this generation as long as you have a good predictor. So in the rest of the presentation, we'll use GFlow nets, we'll use Bayesian optimization. We won't use the diffusion models, but there are a lot of models that are diffusion models that are used to do that. Okay, so going on to the first application. So here we're going to do catalyst discovery, and we'll use Bayesian optimization as our generator. So the motivation for this project is to generate fuel and then maybe eventually jet fuel using CO2 from the atmosphere and renewable energy. So you're trying to convert these molecules into any molecule that contains energy. So often that's a molecule that contains carbon and hydrogen. That's the case for jet fuel. And it's usually longer chains. And so we're trying to achieve longer chains, which means any molecule that has more than one carbon. And so the simplest molecule that has more than one carbon is ethylene. And so in this project, there is an automated laboratory that's at the University of British Columbia. And our goal is to drive this automated lab to optimize all the parameters to get the highest ethylene Faraday efficiency, which is sort of the ratio between how much energy or how many electrons you put in and how many molecules of ethylene do you get out. So this is the setup of the robot. So you give it some conditions, so parameters. You give it the ratio of catalysts that you want. Here we have 2 catalysts, but it could be more. The amount of catalyst, the ionomer, the temperatures, the current, the pressures, there's a lot. I think there's maybe 50 parameters, but we optimize, I think, only 5. So the first thing the robot does is it mixes the metals together and the ionomer. Then it sprays that onto a cathode, which is a carbon paper. Then it brings that to a different station, does characterization. And then finally, it puts that into an electrolyzer and then actually measures the output, measures the Faraday efficiency. And then you can start over as many times as you want. This is what the robot looks like. You can see one of the arms on the left picture, and then the electrolyzer in the middle, and then the right picture is the whole setup. So how do we drive the robot? Well, we do active learning, which means we have data, a little bit of data, we train a model, we make a prediction that gives us what experiment we should try next, and then we try this experiment, and then we add the data to the data set. So for the first step, we have 90 data points, which is not a lot for machine learning, but that's what we have. We started with 90 data points, which means they ran this robot 90 times with sort of random or systematic parameter sweep. Then we created a model. And so we need this model to have the same inputs as the robot, and then to output the same outputs as the robot's Faraday efficiency, plus some level of uncertainty about this prediction. And the way we did this is we started from a physical model of the system that existed in the literature. That's an analytical model. So it takes in a full description of the system, including the thickness of each layer and the size of the particles and the reaction rates, which are all things that we don't necessarily know, especially for each of the experiments. So to go around this problem, we have a machine learning model that takes in the inputs of the robot and then converts that into the inputs of the physics model. So things that we don't know, like rates. And then puts that in the analytical model, which then predicts a Faraday efficiency, which means now we have this loop from the inputs of the robot to the same output of the robot going through a physics model. And this model, because it's analytical, it's differentiable. And as I talked at the beginning of the talk, that's how you train a machine learning model, which means we can train this machine learning model through the analytical model. So now we have the same output as the robot. What we need is uncertainty. So then we put this whole model into a Gaussian process, which will then also optimize for uncertainty and give us, for each prediction, sort of a spread around this prediction. And so what that means is that we can do active learning. And so how do we do that? We do Bayesian optimization. And from the prediction of the model and its uncertainty, we can get something called an acquisition function. So here I'm showing in the full line is the prediction from the model. And then in blue is the uncertainty predicted by the model. And then if you combine this uncertainty and prediction, you can get something like the expected improvement. So at which place, at which part of the space do you have the highest expectation for a better result than the best known result? You could also use something like the probability of improving your best result. So that's what's shown in green. And you can see that the maximum is somewhere where the prediction is quite high compared to the best possible point, and the uncertainty is high enough that it might be higher than the highest point. And this is what you choose as your next experiment. So we haven't been able to do this with the real robot yet for reasons I will explain. But the first step is to actually simulate this within the data we have. So we start from training the model with only a subset of the data we have. And then we ask it to choose within the existing data which data point we should try next. It's like a fake experiment. And then we measure in how many steps does it get to the best possible result in the data set. So if you do this randomly, you get a certain number of steps, which I don't know is around maybe 15 steps or maybe more. It's half of the number of data points. And then you can compare using other models to that reference. So randomly, it would take some amounts of steps to get to the best result. If you use machine learning, a machine learning only model without physics, it's twice as fast. And if you take our model, which is the Gaussian process plus a physics model, it's 3 times as fast as random.
Felix, what do you mean by random here? Do you randomly change the current state?
Random would be, so imagine so we have 90 data points. So we give the model 9 data points. And so if you were to choose data points randomly, you would take all the remaining 81 points and you would take one randomly and add it to your set, right? And at some point by adding randomly, you would get to the best result in the whole data set. And on average, that would take you 45 or, half of the number of data points. So it would take you 45 steps on average. So now we're comparing this 45 steps with using other methods that choose the data points, but in a way that's more smart.
Mm-hmm.
So that means
probabilities in this random, in this finite set of 90
Yeah, this is then a finite set of 90. Yeah.
Okay.
Yeah, so now let's drive the robot. The problem is that while we were working on this model, the robot changed a little bit. When I say robot, I mean the automated lab. It changed to using adsorbed CO2 adsorbed in water, so bicarbonate. So that means that changes the physics, which means that changes our physics model that we need to use. So we're working now on a new physics model that works with this new setup. And we're currently building a general platform that will be able to be used to drive any CO2 reduction automated lab with the same sort of idea and a suite of models, including physics model, but also pure machine learning models. Okay, second application, water splitting, catalyst discovery, and we're going to be using G-flow nets for that. So the motivation for this is production of green hydrogen. So here in Quebec, we use hydroelectricity, 100% or almost. It's almost 100% renewable energy grid, and the energy is extremely cheap. So there's a lot of talk in producing green hydrogen, but even here where energy is extremely cheap, it's only 2% of hydrogen that's produced from water, so from using water splitting. And so that needs to be increased, especially if we want to move towards a hydrogen economy where we replace hydrogen gas. We replace conventional diesel engines with hydrogen. So for midterm energy storage or for heavy transportation, for example. So if we want to get to this hydrogen economy, we need to find a way to produce green hydrogen more efficiently. So the way that the hydrogen is produced is well, you just start from water, you give it electricity, 2.46 volts, and then you get green hydrogen, and the amount of energy that's stored is the amount of energy you put in. That reaction actually happens in two main steps, HER and OER. And usually, so one produces hydrogen, the other one produces oxygen. You need both steps to be happening at once. But usually the OER step is thought to be slower, and both of these, and by slower, that also means you have to put in more energy, so you lose more energy. And both of these require catalysts that are extremely expensive materials. So our goal is to discover new catalysts for water splitting. And we're specifically looking at heterogeneous catalysis. We were using crystal structures, and we want to take advantage of existing data sets in this field, which are the Open Catalyst 2020 and 2022 data sets. So this is sort of our workflow. We have an objective, which is the overpotential, which is the amount of energy you have to put over 2.46 volts. We want to minimize that. That's our objective. We have a generative AI model that I'll talk about, and then hopefully that gets us to the best OER catalyst possible. So first, we'll talk a little bit about the objective. So typically, the way that these calculations are done is you calculate adsorption energies at the surface on a slab surface. So you divide the chemical reaction into multiple steps, and at each step you calculate an energy basically. And then combining these together, you can get an estimate of the overpotential, which again is the amount of energy you have to put over the minimum possible energy for this chemical reaction. So we want to minimize this. The problem is we realize that there's quite high uncertainty on these DFT predictions, or the theoretical predictions themselves that the machine learning models are trained on are quite high. So we estimate that for one adsorption energy calculation in the context of HER, the energy is at least, the uncertainty is at least 0.3 EV. And we estimate that for a more complex OER structure that are often oxides, the uncertainty is as high as 0.5 EV of the DFT prediction itself. So what we did is we looked at the distribution of catalysts inside the Open Catalyst project dataset, which are materials that are chosen randomly. And we measured their overpotential. So the distribution of overpotential is what's shown here in the red box. So here I'm showing a volcano plot. In catalysis, this is sort of the way that it's represented. If you're not in catalysis, it's sort of a counterintuitive way to represent this, I think. So just look at the distribution. We want to have eta as small as possible. We want it to be as close as 0 as possible, which means we want it to be as close as possible to the top. And this is typically how you try to find good catalysts. What we realized is if we went through this data set of DFT calculated catalysts, where the catalysts were chosen randomly, so they're not supposed to be good catalysts, we found that 30% of these randomly chosen materials were predicted within uncertainty as being perfect catalysts. And there's no expectation for randomly chosen materials to be good catalysts. And we did the same things. And yeah, so if you look at some of the materials in this list, there are materials that are obviously not good catalysts for other reasons, like they would explode in water or they would disintegrate. So we think that this objective that a lot of people in this field use is not a very strong filter at all, and maybe we should focus on other objective first, like stability. So we did this for HER. It's sort of a simple way to look at it. We also did this for OER. It's a little bit more complex, but we get the same conclusions that a large portion of the randomly chosen materials are predicted as being good catalysts, which doesn't really make sense if these materials are chosen randomly. So what we did is we looked at other objectives. One objective is stability. And if we measured that instead, so if you imagine measuring that first as a first filter, we found that this is a much stronger filter where only about 5% of materials in these data sets are predicted as being good catalysts. So that's our work on the objective. So a lot of people are using overpotential as an objective, but we are realizing that overpotential is not such a strong filter, so we should add other filters and consider other things than this objective. So for the second part, we'll talk about how we generate materials that optimize this objective. So we use GFlow nets. A GFlow net is a type of generative neural network that generates object step by step, which means if you imagine generating a molecule, it could be something like it adds one atom after the other step by step. If you're generating crystals, in our case, it could be you choose a gravilattice and then you choose a space group and then you choose the composition, something like that. So it's step by step. And if an object is better, it has a higher probability of being generated, which means it doesn't only generate the best material for your objective, it also generates things that are almost the best. So for example, if you had these 3 molecules and you were generating them and you were measuring their performance and try to optimize it, then you would have it would be 9 times more likely to generate this molecule than to generate the one on the right, than to generate the molecule on the left. So this is the whole scheme of how we generate catalysts in this project. So I kind of spoiled it a little bit. The way we construct the object is what's on the left. So the column on the left, we start by choosing a space group, then choose a composition, so the formula, and then we choose the lattice parameters. That gives us a partial description of a crystal. Then we choose the Miller indices, that's the orientation of the surface. Then how we cut the surface, which we call offset. So that chooses the termination. And then on which side of the termination will the adsorbate be put. So now we have sort of a description of a crystal, a space group composition, lattice parameters, Miller indices, offset, and surface. And then we take that and try to build a real crystal with it. So that's the second column. So the first thing is we determine the atomic positions. As you may know, this description doesn't tell you the atomic positions, but we're looking at simpler systems where having the space group and the composition can tell you exactly how the atoms are placed. So we place these atoms in the structure, then we relax the structure using a machine learning force field. So talk a little bit about that. So for each material, you have, you're optimizing something like the lattice parameters with respect to energy. So in green here, you see the potential energy. So you want to minimize that to get all the atoms to have zero forces, basically. So in red, you see what the materials that are generated look like. And then after relaxation, they all end up in the same lattice parameter, which means that even if the lattice parameters are not exactly correct, because of this relaxation, we get it to something more realistic. Then we convert this relaxed structure into a graph and make a prediction of absorption energy, which we can then transform into the overpotential prediction that we're currently using, but we know that we need to move to also including more stability. And then with that, that's our reward function. That's what we optimize. So then we should get crystals that are better catalysts in a higher probability. So for the predicting model, to predict the absorption energy, we just use a machine learning model called FENET that predicts absorption energy. This is showing its performance. And then finally, this is a result. So here we use this scheme to generate catalysts for HER. So do you remember there's two sides of this water splitting, OER and HER. This is the easier part that generates hydrogen. So what we did is we restricted the space to just metals with only a few space groups. And then we tried to see if we would find platinum as being the best HER catalyst, because that is in reality, the best known catalyst. And so here you can see the number of samples generated by our algorithm for each of the metals. And you can see that platinum was the one that was generated the most, which also makes sense with its predicted over potential. And then rhenium is the second one, which also makes sense with the experiment and theory. So this is sort of a proof of concept that with our algorithm, we're able to identify or rediscover the best known catalyst within a small subspace of materials. So now the next steps are to first do this for OER, which is more complex, but also expand the space to a space that contains new elements that might lead to more interesting catalysts that, for example, are maybe cheaper than platinum. So you can see this first proof of concept it's published online. Now I will move on to the last application. So solid-state electrolyte generation with GFlow nets. So again, we use GFlow nets here. We will eventually use GFlow net for this. So the motivation for this one is to work on the next generation of battery materials. So current battery materials use lithium-ion batteries, which are well known. They're very good batteries, obviously, and they're used everywhere. But they have some limitations, like they can catch fire because the electrolyte can burn, and they have good energy density. But we want to get to even higher energy densities. So the next generation, or what's seen as the next generation, is solid-state electrolyte batteries, where the electrolyte, instead of being a liquid, is solid, and it's not flammable. And then that also allows the device fabrication to require less layers, which in turn increases the energy density of the battery. So a promising technology, but what we need is electrolyte materials that are highly ion conductive. So the goal of this project is to discover new materials with high ionic conductivity for applications of solid-state batteries. So yeah, ionic conductivity is how well ions, it's in this case lithium ions, can move inside the material. So the first step for us was to get data, because if we want to do machine learning, we need data. And so we created this data set called OBELiX that combines different existing data sets, but a lot of data from the literature into a data set of crystal structures that are labeled with experimental ionic conductivity. Here, these are just a few statistics about the data set. You can go look at it. You have the distribution of log ionic conductivity here, and we split this into a test set and a training set. What's interesting about OBELiX is that there are a lot of materials in this data set that are repeated. So here, each vertical line is a group of materials that are repeated. So it's the same material that was measured experimentally by different groups at different time and different experimental conditions. And then the y-axis is the ionic conductivity. So you can see, and then it's just ordered. You can see sort of the spread between each of these data points, which are supposed to be exactly the same material. And here, this is showing the spread with respect to the mean of each of these little groups. And with that, we can measure some sort of spread, and we get to about 0.4 orders of magnitude, which gives us an idea of the experimental error on measuring ionic conductivity. So 0.4 in log space, 0.4 orders of magnitude. So that's already quite large, but this is kind of the best we could ever do. So what we did is we benchmarked different machine learning models on our data set. So here we're showing the mean absolute error, so sort of the performance, the lower the better. That dashed line is this experimental error, which is something we don't think we can beat because the data has this much error in it. And then we did some different training strategies for each of these models. And in blue is the validation performance, and in red is the test performance. So we held out a few materials that we didn't train on, and we made sure that these materials were different from the training materials. And then the dashed line at the top is the median estimator, which means if you were just to predict the median every time. And you can see that the performance of these models, even though those are state-of-the-art, very large models, is in a lot of cases worse or equal to a median estimator on the test set, which means that it learned very little about the data set. And that's an interesting result, because if you compare that to smaller models, so those are the two on the right, that use just less weights and parameters. So a MLP is a very simple neural network, and then a random forest. And we trained on these, and you can see that the performance is much, much better. So that's an interesting result, because it shows that if you have very small data, it's probably better to use a smaller network, but it also shows that predicting ionic conductivity is a difficult task. So now our goal is to have sort of a suite of models that take more or less time and are more or less accurate. So if you look at the top here, the best possible way to measure ionic conductivity is obviously to measure it experimentally. And we know that this is going to be about 0.4 orders of magnitude in terms of accuracy. And that can take months to even years to make these materials and measure it. Then you can make theoretical predictions. So we're also working on that, that are based on forces, so molecular dynamics. So you can use ab initio molecular dynamics, so using DFT, and make predictions. And we're not sure yet. We're trying to measure on our data set what is the accuracy of DFT in making those predictions, but those predictions are so slow and so time-consuming that we are not there yet. We don't know, but we think that it will be about 1 order of magnitude in terms of accuracy. And then for each material, it takes multiple days, and maybe less than a week, to do one single ionic conductivity prediction. The other alternative is to use machine learning force fields to do the molecular dynamics. And this is what Dunia, my intern, is working on. Here you can see a parity plot. This is using MACE foundation model to make ionic conductivity predictions. This is the expected one on the x-axis and the predicted one on the y-axis to make the ionic conductivity prediction. And you can see that for some materials it works sort of well, but the error is quite large. If we measure this error directly, it's even worse than for the neural networks that I showed before. So it's a difficult prediction to make, and we're using fine-tuning to see if that can improve the predictions. So this is one thing we're working on. That takes on the order of minutes to hours to make one prediction. So I think maybe less than an hour to make a prediction for one material. Then the neural networks that I showed before, the best one was the random forest that had about 1.8 orders of magnitude in terms of accuracy. And then the worst case scenario is just we just predict always the same thing. and we know that this is about 2.8 orders of magnitudes. So what's the goal of having all these models? Well, if we want to do active learning, there's a thing called multi-fidelity active learning, where we can choose, the neural network will not only choose which experiments to try, so which material to try next, but also with what model. So for example, if you're very confident that a material is good, you could choose to try it in experiment. If you're somewhat confident, you could try to use machine learning to verify it, or machine learning force fields to verify it. And if you're unsure, or as a base model, you could use a neural network that directly predicts ionic conductivity. So this is sort of our ultimate goal, is to use this model that already exists, that's called multi-fidelity active learning with GFlow nets, where we would have a model that makes these choices of what experiments, but also what models to use. And so, yeah, that was it for all of our projects. So the takeaways, if you have a predictor of a property, you can turn it into a generator. Molecule and material generation requires models that are robust and objectives that make sense. We talked about how it matters to have the right objective for catalysis, and how generators can trick the predictor models. We've made a physics-informed model for CO2RR that can accelerate finding the best possible experiment. We found that the objective of absorption energies and overpotential is not a very good filter for finding good catalysts. We've done a proof of concept using GFlowNet to rediscover platinum as the best HCR catalyst. And I just presented our OBELiX dataset, which is a dataset of experimentally measured ionic conductivities and crystal structures. So thank you very much, and I'll be happy to answer your questions for the time that's remaining.
Thank you very much, Felix. Please thank Felix physically, virtually. And I'll stop recording.